Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the grand tapestry of early 20th century physics, certain moments radiate with a brilliance that redefines the entire intellectual landscape. The year 1905, Albert Einstein's Annus Mirabilis, stands as a monumental peak, a year in which the young patent clerk dismantled classical certainties about time, space, and light. Yet, the narrative of relativity's ascent often leaps from this precipice of special relativity directly to the majestic summit of general relativity, fully realized in 1915. This conventional telling overlooks a crucial, formative period of intense intellectual struggle and profound insight, a period crystallized in a 1908 paper that serves as the essential bridge between the two theories. The work in question, properly titled Über das Relativitätsprinzip und die aus demselben gesehenen Folgerungen or on the relativity principle and the conclusions drawn from it, represents far more than a mere summary of its 1905 predecessor. It is a work of synthesis, clarification, and, most importantly, radical extension. Within its pages, Einstein took the first, tentative, yet conceptually decisive step beyond the comfortable confines of uniform motion, confronting the far more complex and universal phenomena of acceleration and gravity. This essay will explore the 1908 paper as a pivotal document, examining the intellectual soil from which it grew, the revolutionary seed it planted with the equivalence principle, its relationship to the parallel geometric formalization of spacetime, I. Hermann Minkowski, and its ultimate role as the conceptual touchstone for the decade-long odyssey that culminated in the general theory of relativity. The intellectual environment following 1905 was one of profound, if localized, upheaval. Einstein's special theory of relativity, articulated in On the Electrodynamics of Moving Bodies, had provided a stunningly elegant resolution to the conflict between Newtonian mechanics and Maxwell's equations of electromagnetism. By positing the constancy of the speed of light in all inertial frames and the principle of relativity, he had successfully reinterpreted the Lorentz transformations, which were developed by Hendrik Lorentz and Henry Poincaré, moving them from mathematical curiosities designed to explain the null result of the Michelson-Morley experiment into direct consequences of the fundamental structure of space and time. This deposed the luminiferous ether, that hypothetical universal medium, from its privileged position in physics. The theory, however, possessed a clear and self-imposed limitation. Its principles applied exclusively to inertial frames of reference, those systems moving at a constant velocity relative to one another. The universe, of course, is replete with acceleration-spinning planets, orbiting moons, and objects falling under the pull of gravity. This omission was a source of deep intellectual dissatisfaction for Einstein. His 1905 theory, for all its power, felt incomplete, a special case within a much grander, yet undiscovered, physical reality. The 1908 paper was his first published attempt to generalize his principle, to explore whether the beautiful symmetries of relativity could encompass the messy reality of acceleration and, through it, the ancient puzzle of gravitation, a force that Isaac Newton had described with impeccable accuracy but had left fundamentally unexplained. The centerpiece of the 1908 paper, and arguably one of the most sublime thought experiments in scientific history, is the introduction of the equivalence principle. Einstein himself would later call the insight that sparked at his glücklichste Gedanke his happiest thought. He imagined an observer inside a closed chamber, a windowless chest or elevator, in a region of space far from any gravitational influence. If this chamber were to be accelerated upwards by some external force at a constant rate, an object released by the observer would fall to the floor in precisely the same manner as it would in a stationary room on the surface of the Earth. The observer, confined within the chest, would have no experiment capable of distinguishing between the effects of a uniform gravitational field and the effects of a constant acceleration. From this simple, powerful observation, Einstein postulated a profound physical principle: the complete physical equivalence of a gravitational field and a corresponding acceleration of the reference system. This was a radical departure from the Newtonian view, where gravity was a force acting at a distance. In Einstein's nascent vision, gravity was becoming a feature of the reference frame itself, a kind of fictitious force akin to the centrifugal force experienced in a spinning carousel. The paper then boldly explores the consequences of this principle. If acceleration can warp the measurement of time, as special relativity had already shown, then gravity must also warp time. Einstein predicted that a clock in a strong gravitational field, such as on the surface of the Sun, would run measurably slower than a clock on Earth. Even more astonishingly, he reasoned that light itself must be affected by gravity. A beam of light traversing a gravitational field would follow a curved path, a prediction so counterintuitive it bordered on the absurd for most of his contemporaries. The 1908 paper laid out these predictions, derived from a single, elegant principle, thereby transforming gravity from a force into a manifestation of the geometry of spacetime, though the full mathematical language for this transformation was years as Einstein forged this new physical intuition in 1908. A parallel and equally profound development was unfolding in the realm of mathematics. In a famous lecture delivered in Cologne, the mathematician Hermann Minkowski, one of Einstein's former professors, provided a revolutionary geometric interpretation of special relativity. Where Einstein had worked primarily with algebra, Minkowski envisioned a unified, four-dimensional continuum he called spacetime. He declared with theatrical flair, henceforth space by itself, and time by itself, are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. Minkowski demonstrated that the Lorentz transformations were equivalent to rotations in this four-dimensional spacetime. The quantity that remained invariant, that all inertial observers would agree upon, was the spacetime interval. This interval, let us call it delta S, is given by the relation delta S squared equals the sum of the squares of the spatial separations, delta x squared plus delta y squared plus delta z squared, minus the product of the speed of light squared and the square of the time separation, c squared times delta t squared. This formulation provided a powerful, abstract, and deeply beautiful geometric foundation for Einstein's physical theory. Curiously, Einstein's initial reaction to Minkowski's formalism was one of dismissal. He regarded it as Überflüssigkeit, Gelehrsamkeit, or superfluous learnedness. This touch of historical irony is telling. Einstein, the physicist driven by concrete physical principles, initially failed to appreciate the power of the mathematical abstraction that would later prove indispensable for the development of general relativity. The geometry of a flat, Minkowskian spacetime was the perfect stage for special relativity, but for a theory of gravity as curved spacetime, a far more sophisticated geometric toolkit would be required. The immediate impact of the 1908 paper was confined to a small, elite circle of theoretical physicists. Max Planck, a crucial early supporter of Einstein, recognized the paper's significance and engaged with its ideas. However, the predictions it contained, particularly gravitational time dilation and the bending of starlight, were far beyond the reach of contemporary experimental techniques. Its primary and most enduring legacy was the effect it had on Einstein's own research program. The equivalent principle became his guiding star, the central axiom that would lead him through the wilderness. It set him on a relentless quest. A nearly decade-long intellectual marathon defined the mathematical equations that would describe how mass and energy dictate the curvature of spacetime. This journey was arduous and fraught with missteps. The key breakthrough came when Einstein finally recognized the necessity of the mathematical language he had earlier dismissed. He sought the help of his friend Marcel Grossmann, a mathematician, who introduced him to the arcane world of differential geometry and tensor calculus developed by Bernhard Riemann, Gregorio Cicabastro, and Tullio Levi-Civita. This was the precise mathematical framework needed to describe a curved, four-dimensional manifold, a structure where the simple geometry of Minkowski's spacetime gives way to a dynamic landscape whose contours are shaped by the presence of matter. The conceptual seed planted in the 1908 thought experiment could only reach full flower in the rich soil of Riemannian geometry, demonstrating a profound and necessary synergy between physical intuition and mathematical formalism. The path from the principle of equivalence to the final field equations of general relativity was anything but direct. The principle itself underwent refinement, evolving from the weak equivalence principle, the observed equality of inertial and gravitational mass which had been tested with increasing accuracy since Galileo, to the strong equivalence principle, which posits that the laws of physics themselves are the same in any small, freely falling reference frame as they are in special relativity. This stronger version is the true heart of general relativity. Einstein and Grossmann's early attempt, the so-called Entwurf or draft theory of 1913, contained a significant conceptual flaw, failing to achieve general covariance, the requirement that the laws of physics take the same mathematical form in all coordinate systems. This failure led Einstein down a difficult path for 2 years, a period of intense frustration, before he finally identified and corrected the error in a flurry of activity in late 1915, culminating in the presentation of the correct field equations to the Prussian Academy of Sciences. These equations, symbolically represented as r sub mu nu minus 1/2 times r times g sub mu nu equals 8 pi g over c to the 4th power times t sub mu nu, elegantly connect the geometry of spacetime on the left side with the distribution of mass and energy on the right. The ultimate vindication of the idea first floated in 1908 came in 1919. An expedition led, by the British astronomer Sir Arthur Eddington travelled to the island of Principe to observe a total solar eclipse. By measuring the apparent positions of stars near the sun's limb, Eddington's team confirmed that starlight does indeed bend as it passes through the sun's gravitational field, and by the precise amount Einstein's full theory predicted. This dramatic confirmation, announced to a world wearied of war, transformed Einstein from a renowned physicist into a global cultural icon and cemented gravitation as a property of curved spacetime. In conclusion, Einstein's 1908 paper on the relativity principle and the conclusions drawn from it occupies a unique and foundational position in the history of modern physics. It is a work of profound transition, capturing the exact moment when its author recognized the inherent limitations of his own celebrated special theory and embarked upon the monumental task of its generalization. The paper's enduring contribution is the equivalence principle, a conceptual leap of breathtaking simplicity and power that reimagined gravity itself. This principle, born from a humble thought experiment about an observer in a box, provided the physical intuition that guided Einstein through the labyrinthine mathematics of tensor calculus and toward the final formulation of general relativity. While Minkowski's concurrent geometric insights provided the formal stage, it was Einstein's 1908 physical principle that wrote the first act of the play. The paper stands as a testament to Einstein's distinctive genius, his ability to derive universal-altering consequences from simple, foundational postulates. It is the intellectual nexus point, the indispensable link connecting the special case of 1905 to the universal theory of 1915, and as such, it remains a document of singular importance, revealing the genesis of our modern conception of the cosmos.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.